Now, for the sake of completeness, I'd like to take one more step, a final step, and complete our discussion of viscoelasticity. Viscoelasticity is a nice topic in the sense that you might have realized that as we progress more and more away from the topic of elasticity, we have more and more experimental input, phenomenological input into our models through functions that are heavily motivated and eventually formed through experimental data. Now, experimental data is always something we need, but in the case of elasticity, the amount of experimental input into the mathematical form is minimal. We just have a number of constants which appear in a compliance matrix, say, and then that defines stress-strain relation. Now, viscoelasticity is in some sense similar and quite mathematical, and it's appropriate, let's say, generalization to capture experimentally observed behavior can be carried out in a similar, very mathematical fashion. So, for instance, if we want to capture anisotropy, we know how to go from generalized Hooke's law formulation to the Foyt notation and introduce the compliance matrix. Now, in the case of viscoelasticity, there is a, let me say, in some sense, a similar generalization. First of all, viscoelasticity can also be anisotropic. That's not what I'm talking about. As we've done in almost every instance except for the explicit anisotropy discussion, we are stuck, or we are limiting ourselves to the range of isotropic material behavior. But what I mean is a generalization that is fundamental to capture some physics that is of essence. And let's talk about that. In other words, let's talk about the relaxation. I will say relaxation times, or let's say spectrum. So in other words, a range of times, a certain number of values. And it will become clear what I mean by that in a second. So essentially the motivation about what I'm about to talk about is the SLS model, and the fact that it's perhaps a little bit too simplistic. Remember the SLS model. We have a spring on its own. That's the rheological model of the standard linear solid representation of viscoelasticity. We have some strain or stress input. We want to measure the other one, and the material properties are E infinity, and then those that appear within the Maxwell branch. Let's indicate the Maxwell branch just for the sake of this discussion with a box. I know that there is a spring in there together with a dashpot. The spring has a Young's modulus E, and the dashpot has a viscosity. But instead of identifying what the viscosity is directly, I'm just going to write the ratio of that to E, in other words, the relaxation time. And I will call this the Maxwell branch. Okay, so that's the buck that contains the Maxwell branch. And the signature of the behavior that is implied by the SLS model is a relaxation function that is of the form E infinity plus E to the minus t over tau, where tau is the relaxation time. All right, so now let's go back and let's go ahead and remember what the type of relaxation function we observe is. Well, the type of behavior we observe is where on a log-log scale, so first of all, the vertical scale G, irrespective of whether it is temperature or time, it's always log of, on a log scale, the relaxation function. So now in this case, on the horizontal axis, we have time, say in seconds, and we know that the material is going to start off as stiff. So that's E infinity plus E, and eventually end up behaving soft. That is E. All right. So the behavior which I observe is this. Now, the way I'm drawing it before was perhaps a bit exaggerated, the way this decay was happening, to highlight a number of features there. Here, perhaps this is a bit more realistic. If you plot this function on a log-log scale numerically, this is closer to what you will observe. Notice that the distance between the top line and the bottom line here is exactly equal to E, the Young's modulus that appears in the Maxwell branch. That's the amount by which the relaxation function decreases. Now, let's say that this is the value, the variation of G for a given relaxation time, because eventually, ultimately, the way that decay occurs certainly is going to depend on the value of the relaxation time. If it is small, it's going to look like this. If I pick it to be larger, that decay is going to occur at a later time. So the material will remain stiff for a longer extent, and then eventually, however, exactly the same type of behavior will occur. So this is, if you like, standard linear solid model 1. This is standard linear solid model 2. The only difference between the two models is the fact that the first one is identified with one relaxation time that is smaller than the value of the relaxation time in the second case. So the second model has just exactly the same setup but with a larger relaxation time. So therefore, you might think that by playing with the value of E infinity and E, which determines the bounds of these lines, and by determining the correct relaxation time, you can capture any viscoelastic material behavior, because I told you the relaxation function is the signature of a polymer or viscoelasticity, and therefore to capture that signature, my parameters are E infinity E and the relaxation time, which determines where this decay is going to take place. Now it turns out that the first aspects determining the bounds is a realistic approach. So in other words, you can do a test on a polymer and you can load it so fast through a constant strain, immediately measure the stress, take the ratio, give it no time to relax. You can find the stiff behavior. This is the stiff behavior and this is the soft behavior, right? So you can load it very, very fast so it has no time to relax. So at that very small time scale, if you're all the way down there, remember this is logarithmic, then you can determine what this stiff bound is. Now, ultimately, you can also do the following. You can pull and wait forever and find the ratio of stress to strain in relaxation experiment and measure E. So you can determine these 2 bounds. And now you have those two values, and then you now do a test where you carry out the relaxation. And it turns out the type of material behavior you observe is as follows. Okay? So this is more close to reality. Now, this is strange, and the reason it's strange is it seems my SLS model is able to capture the 2 bounds, but the decay rate it's predicting on the log-log scale is very fast, whereas in reality it's not as fast. Now, I can play with the relaxation time, but all that's going to do is it's going to shift this black line left or right, whereas reality is just a line that decays slower. Well, that indicates that probably I need to generalize my model of viscoelasticity beyond what standard linear solid model implies. And so the outcome of this is that the SLS model is perhaps too simple. With respect to what? With respect to real experimental observations. Certainly, this is a good point to start from and could have been sufficient for our purposes as well to a large extent, but let's proceed a little bit just for the fun of it. So what we want to do now is we would like to complicate the SLS model a little bit further. And the way I'm going to do that, and let's just do a qualitative discussion, and if you're interested, then you can carry out a detailed mathematical description of what is going on. And the way I'm going to calculate it is as complicate it is as follows. Now, first of all, I remember that if I want to complicate this model, I can put more springs in series, but really I just can combine everything into a single spring, an equivalent spring, so that doesn't really help. I don't want to add a dashpot in parallel because that wouldn't be a good viscoelasticity model as we discussed all the way at the beginning. So if I want to stick to this type of parallel structure, what I want to do is, perhaps, I want to go ahead and enrich the upper part. So in other words, I want to take more of these, okay? I want to add things in parallel, but those things should be combinations, serial combinations of, let's say, of Maxwell branches, okay? This is one way to do it. So in other words, I will not have a single branch of Maxwell element, but I will have multiple of them. Let's put 2 and see what happens. Okay, so now this is our rheological model. Always remember, dimensions have no importance. It's just the mathematical description between stress and strain that this model implies is what counts. So now we have a Maxwell branch where there is a E and a tau, or E and a viscosity equivalently, but those values do not need to be the same. So in other words, there can be now a Young's modulus, let's say 1, and relaxation time 1, and a Young's modulus 2 and a relaxation time 2, which do not need to be the same. Now I know that eventually my polymer is going to start by, I go back and immediately correct a typo that I saw. This should be E infinity. I know that the polymer is going to display a behavior where it's going to start from a stiff value and go back to a final soft value. That soft value I already captured in the model. So now I have 2 boxes, 2 relaxation times. I want to choose, however, the E1 and E2 such that they sum to E, because E is the amount by which this drop occurs, and that I can easily identify through the experiment. So as I enrich, okay, I know that the upper bound is E plus E infinity and the lower bound is E infinity. The decay is by a certain amount, and when I pick E1 and E2, I'm going to pick it to be so that the sum is always equal to the amount that I have observed, which I called E, okay? So now, why am I saying that? Because then now you can go, now first of all, we have 2 branches, 2 relaxation times, and 2 Young's moduli such that they satisfy a certain experimental observation. And now why is that observation important? Because if you now go to a mathematical analysis of this, really it's not hard, right? So now this is the total stress, say, you want to measure, and that's the sum of the stress here and there and there, okay? But now, just like we assigned previously the viscous and an elastic strain to each spring and dashpot that we had, here you can go and do the same. But the amount of elastic strain here and there and the viscous strain here and here therefore are not the same. The total strain is always the same, and therefore you'll end up having 2 differential equations that govern the viscoelastic strain within each Maxwell branch. And so you can show eventually, I will say easily, really, fairly easily, you can show, and go ahead and try to do that if you want to, that the relaxation function in the present case is going to look as follows. Now, if there was only one, it would be E minus T to the power minus T over tau. But now I'm gonna have 2 of those because there are 2 branches, one with 1 relaxation time, 2 with another relaxation time. And now the same type of range or limits that I can observe classically also applies here. If t is equal to 0, then I have E infinity plus E1 plus E2, and I just called that E infinity plus E because that's what the sum is by my definition. And as t goes to infinity, g takes the value, this dies away at different times perhaps, but eventually I die to g dies to E infinity value. And the jump is through the value E that I have observed experimentally, and that's why I enforce E1 and plus E2 to be equal to that observed value. So now let me go ahead and plot that. Again, it's a relaxation function. Now it's not the relaxation function, the classical one. It is one where there are 2 relaxation times. Let's go ahead and plot that. So it's going to be, again, always log scale. This is log, and this is time, and this is g of t. And well, starts off with E infinity plus E, dies down to E infinity, okay? And now let us assume that, just for the sake of discussion, that tau 1 is less than tau 2. First of all, if they are the same, in other words, I can choose different E1 and E2 and different eta 1 and eta 2, but if the ratios are the same, if tau 1 is equal to tau 2, then these factors are the same. There is just one relaxation time. You can take this exponent outside, some E1 and an E2, you're back to this function. So you don't want to choose them the same. It doesn't make sense. It's not generalizing, it's just complicating it unnecessarily. So if they are of this fashion, on the other hand, the way the decay will occur is as follows. So first of all, let us take an intermediate step. That intermediate step is E infinity plus E2. In other words, because I'm assuming tau 1 is less than tau 2, this one's gonna die first. This one's gonna die, and I'm gonna left with this. So it's as if momentarily we have a very fast decay towards the value at E infinity plus E2. That term has died away. And for a while, tau 2, if it's large enough, this term, the second term, is not going to be activated. Just like when the time is not large enough, you remain at a constant stiff value. You're going to remain at a constant intermediate stiffness. But then eventually, when the time reaches tau 2, then you're going to have a significant decay. So this portion here, this here is of the order of tau 1, and that here is of the order of tau 2, and individually they are fast decays. Okay, so well, great, that looks great. So we have some intermediate jump of magnitude E1, another jump eventually of E2, sum them up, that's E, that's the observation that I made. Now let's go ahead and observe reality once again. The reality is this. So that is reality. And now I'm going to ask you a question. Now what I was able to do was, if I had, forget about the one of the black lines here, if I had a single relaxation time in the standard linear solid model, then I get this black line, which is far from what I want. Reality is much more spread over time on the log scale. So then I go ahead and put 2. When I do that, I spread it out a little bit, but still it's not good enough. Here I capture a bit of it more. Here I am able to now have something, whereas here, in this case, it's either that you capture a little bit here and none the remaining, or here you capture a little bit in the middle, just a little bit, really not so good, but nothing here or there. It's a really terrible fit. Now here, this, you see, this black line is a better black line than either of these. So putting 2 relaxation times is better than putting 1 relaxation time, but still it's not good enough. It's not reality. So my question is, a single relaxation time is obviously not a good representation of polymer behavior, viscoelastic behavior in a theoretical setting, and doesn't match experimental result, which is reality. And 2 appears to do somewhat better, still not good enough. So the question is, how many relaxation times does a real polymer have with the meaning of relaxation time that I've described here? How many relaxation times do you think it has? Okay. So if you've thought about that question, well, the answer is a lot. In fact, we can theoretically say, as the answer typically is to such questions in our course, the answer is either infinitesimally small or the reverse of that, infinitely many. So in this case, infinitely many relaxation times. So let me draw the relaxation time once again, relaxation function, and let me explain what I mean by that. Now, what I can observe experimentally and rather easily to within a good approximation are first these 2 bonds. I loaded very rapidly, measure the ratio of stress to strain, that's what it is. I loaded extremely slowly. I wait forever, and that I measure as well. So I know how much of a jump I expect to see. That's through E, as I've already used. Okay. And then I do an experiment, and the experiment reveals that the variation is very smooth, like that. Shouldn't have really gone below the green line. That was my typo. Let me correct that if you like. Good. Okay. So, and then it remains there. Well, now I want to capture that line. Now what I can do is I can start off with such a model and put many, not one, but many branches, such that the sum of the Young's moduli of the branches is always equal to the Young's modulus. So sum EI is equal to E. I goes from 1 to 2 to whatever number of branches I have. I don't know. So it's just a qualitative way to depict it. But the relaxation times are always ordered in some fashion. So they are increasingly getting higher. Okay, so now there is among these a relaxation time tau 1, which is associated with the Young's modulus E1, a value that's going to cause a tiny decrease in the value of the relaxation function at the corresponding relaxation time tau 1, roughly at that time. But then it doesn't have to wait so long, not that much. Immediately afterwards, there's going to come a tau 2. And then immediately afterwards, a tau 3, and a tau 4, and a tau 5, and a tau 6. And this way, I could go on forever. Okay? So this is the type of curve that I observe by using many Maxwell branches. And so you see that if I increase the number of Maxwell branches by adjusting the values of those E's and taus, I can get closer and closer to reality. The blue is my model. The red is experimental reality. So in the limit of infinitely many branches, I can capture a very smooth line, which indeed is, in some sense, what one ultimately can do as the best model in a theoretical setting at least. Okay? But even then, we see that the SLS model is good, provided that instead of one relaxation time, I use sufficiently many to capture that behavior. In fact, in many cases, in a numerical setting, an experimental, a numerical scientist or design engineer, in order to model the behavior, that's what they would do. They would use just this model, exactly something like this, with more than 2 relaxation times, so that they capture this spectrum of relaxation times that a polymer displays in reality. And by playing and engineering those relaxation times, they essentially engineer, let's say, how a tire, a structure that is dominated by viscoelasticity, eventually performs and delivers a reasonable performance, depending, of course, on the engineering application that you're seeking. Okay? Let us finally conclude by the observation that reality can be captured by this model, provided you do it carefully to, of course, always to within some modeling quality. This blue line, for instance, might be acceptable for some instances. For some instances, you might require more. And for some instances, something as simple as SLS, which we have gained more experience in, might actually be sufficient enough to give you a good idea of what is going on with this structure that is governed by viscoelasticity.